Now, this is quite a story from NASA because for the second time in history, a man-made object has left our solar system. NASA is saying the Voyager 2 probe is now in a space between the stars after exiting the sun's protective bubble, which is called the heliosphere. Voyager 2, the Intrepid spacecraft launched in 1977, has once again defied expectations and shaken the foundations of space science. After decades in space, having traveled more than 12 billion miles from Earth, it recently transmitted data from a region far beyond the known planets, a place where sunlight is but a whisper, and the rules of space seem almost rewritten. The discovery it made at the edge of the solar system was nothing short of staggering. Voyager 2 encountered a region of space where the fundamental behavior of particles, magnetic fields, and plasma flows contradicted every prediction scientists had made. This wasn't just a surprising twist. It was an impossible one based on our current understanding of physics. Before we start, smash the like and subscribe buttons for more updates. As Voyager 2 drifted further into interstellar space beyond the Heliopause, the boundary where the sun's influence fades into the interstellar medium, it began detecting strange anomalies. Sensors built to measure charged particles, cosmic rays, and magnetic fields began transmitting data that didn't make sense. Cosmic rays, which were expected to be relatively evenly distributed, instead surged in strange waves, pulsing and receding in irregular intervals. The magnetic field, rather than weakening and diffusing as anticipated, grew stronger and more ordered. Even more bizarre, high-energy particles seemed to be bending around Voyager 2 as if responding to some unseen force or structure in space. This deviation from the norm wasn't just a hiccup in the data. It persisted, patterned, and consistent, demanding serious attention. The idea that a spacecraft could cross the heliopause and find a sharply defined and organized magnetic field defied decades of models. Voyager 2's onboard magnetometer recorded a jump in field strength that no simulation had ever predicted. The intensity of the magnetic field was nearly 3 times stronger than what Voyager 1 had observed when it crossed into interstellar space years earlier, and the direction of the field was completely different, suggesting that the two probes might not even be entering the same kind of interstellar environment despite being relatively close in cosmic terms. At first, some scientists suspected an instrumentation error. Voyager 2 is over 45 years old after all, operating on an ancient radioisotope thermoelectric generator and designed with 1970s-era electronics. But multiple checks confirmed that the instruments were functioning exactly as they should. The signals were real, and they described a phenomenon entirely outside the realm of current heliophysics. The shock was palpable. What Voyager 2 was seeing wasn't just new, it was impossible. One of the most stunning findings was the behavior of the plasma that drifts through this remote boundary. Plasma, the hot ionized gas that comprises much of the universe, should have been sparse and sluggish in this region. Instead, Voyager 2 found it to be denser and colder than anticipated, almost as though it had passed into a kind of invisible buffer zone between the heliosphere and the true interstellar medium. This plasma didn't behave like the solar wind, and it didn't behave like interstellar plasma. It was something in between, caught in a strange liminal state that had never been observed before. This unexpected zone, denser than the solar wind and yet too cold to be driven by the sun, raised immediate questions. Was there a kind of interstellar sheath wrapped around the solar system, a previously undetected layer separating us from the broader galaxy? Adding to the mystery was the way radio waves propagated through this region. Voyager 2 had been periodically pinging signals back to Earth, and these transmissions started bouncing back with subtle distortions. Scientists analyzing these radio echoes discovered frequency shifts and phase modulations that hinted at unusual structures in the plasma, like eddies or folds in the fabric of space. These weren't the kind of variations one would expect from a simple homogeneous cloud of interstellar material. They pointed toward a dynamically complex, possibly layered structure at the edge of the solar system. And if such a structure existed, it meant the heliopause wasn't a simple boundary. It was a frontier of active, perhaps even protective properties. Magnetic reconnection events, where magnetic fields snap and realign, were another startling feature of this boundary region. Voyager 2 detected rapid, sharp changes in magnetic polarity, events that released bursts of energy previously believed impossible so far from any stellar body. These magnetic anomalies echoed some of the most powerful forces observed near stars and black holes, except they were happening in what was thought to be relatively calm space. The implications were enormous. If the edge of the solar system can host such events, then it might not be as passive and inert as once thought. In fact, the solar system's boundary could be a place of fierce electromagnetic activity driven not only by the sun, but also by interactions with the galactic environment. But perhaps the most difficult piece to reconcile was the unexpected directional shift in cosmic ray distribution. Voyager 2's cosmic ray detector observed a persistent asymmetry. More high-energy particles were arriving from one direction than from any other. These weren't solar particles, they were galactic, some possibly extragalactic. Yet they were being focused like a lens, or filter was shaping their approach. This directional bias was not predicted by existing models of interstellar space. It suggested that something out there, possibly a massive magnetic structure or even a gravitational feature, was altering the trajectory of these high-energy particles. If such a mechanism exists, it could mean that the solar system is surrounded by an as-yet undetected force field, a relic of galactic magnetic topology, or perhaps something even more exotic. This possibility led to wild but scientifically grounded speculation. Could the sun's movement through the Milky Way be stirring up a magnetic wake like a boat crossing a lake? If so, maybe Voyager 2 has entered this wake, an unseen structure where magnetic fields converge and twist. Alternatively, perhaps the galaxy itself has a skeleton of magnetic filaments like invisible scaffolding, and Voyager 2 has just brushed against one. The idea that there are vast magnetic structures in interstellar space, stable and powerful enough to influence plasma and particles at such great distances, challenges the very way astrophysicists understand the interstellar medium. Not only are these findings revolutionary in a theoretical sense, they also force a reevaluation of the solar system's relationship to the galaxy at large. For decades, scientists have treated the heliopause as a kind of end of the road, a loosely defined edge that marked the transition from solar to galactic influence. But what Voyager 2 is revealing now is something far more complex and dynamic. The boundary may act less like a fence and more like a membrane, semi-permeable, reactive, and variable over time. And if the heliopause can change so dramatically, it raises a terrifyingly beautiful possibility. The solar system is not an isolated bubble, but an active participant in a larger galactic ecosystem. One of the more intriguing implications centers around the possibility that these structures could shield or expose the inner planets to dangerous radiation. If the outer boundary of the solar system can bend cosmic rays, then it might act as a kind of cosmic weather shield. But this shield is not constant. As the solar system moves through the galaxy, encountering clouds of gas, magnetic fields, or dark matter, this boundary could shift, exposing the Earth and its neighbors to increased levels of radiation. This might have direct consequences for the climate, biological evolution, or even mass extinctions over geological timescales. In other words, what Voyager 2 has found could be the missing piece in understanding how galactic scale forces influence life on Earth. Even more provocatively, there's the suggestion that what Voyager 2 is encountering might be a previously undetected phase of matter or a new state of plasma. The idea of a third kind of plasma, one that's neither solar nor interstellar, is entirely novel. It might represent a transitory phase that only exists in boundary regions, or it might be a stable state we simply couldn't detect from within the solar system. Either way, its existence opens the door to a new category of physics, something that could redefine the way we classify cosmic matter. The fact that such a discovery was made by a decades-old probe using 20th century technology only deepens the sense of wonder and curiosity. And then there's the unnerving idea that we might be witnessing the result of phenomena that originate outside the natural world. While still firmly within the realm of speculation, some researchers have floated the idea that the unusual structures Voyager 2 is sensing could be artificial, or the remnants of some ancient astrophysical engineering, vast and long dead, but still influencing the shape of space. Such a notion remains unproven and deeply controversial. But the very fact that it must now be discussed shows how profoundly Voyager 2's discovery has pushed the boundaries of mainstream thought. What Voyager 2 has stumbled upon may ultimately be seen as one of the most important scientific revelations of the 21st century. Not because it gave clear answers, but because it raised better questions. The impossible nature of its findings, denser plasma, reversed magnetic fields, directional cosmic rays, and distorted radio signals, indicates that we've only just begun to grasp the full architecture of our galactic neighborhood. Every new byte of data from that tiny, aging spacecraft brings with it the promise of more secrets, more disruptions to our models, and more reasons to remain endlessly curious. Voyager 2's impossible discovery has shifted our cosmic perspective. It reminds us that even after centuries of charting the heavens, we remain at the beginning of understanding the universe. The edge of the solar system, once thought to be a quiet and featureless horizon, now stands revealed as a dynamic, unpredictable realm filled with forces we barely comprehend. With every signal Voyager 2 sends home, humanity is forced to rethink its place, not just in the solar system, but in the galaxy beyond. And in that small window between the known and the unknown, wonder thrives. Voyager 2's detection of this uncharted region at the solar boundary has not only overturned long-standing assumptions about space physics, but also initiated an entirely new domain of inquiry, one that was previously considered irrelevant because it was deemed impossible. With this surprising development, researchers are now faced with a deluge of data that simply doesn't match established models. The flow of particles, the pressure gradients, the waveforms of energetic electrons, and the peculiar interaction patterns among magnetic fields are all behaving in unprecedented ways. This level of complexity suggests that the heliopause isn't simply a passive border, but a transformative zone, a place where solar origin material undergoes strange transitions as it becomes part of the interstellar environment. Among the most fascinating elements emerging from Voyager 2's recent transmissions is a discovery involving wave-particle interactions never before observed in such regions. Essentially, these are interactions where particles ride along magnetic or electric field waves in ways that cause them to accelerate or decelerate. Previously, such interactions were thought to only occur near strong gravitational or electromagnetic sources like stars or compact objects. But Voyager 2's instruments captured a new kind of wave-particle resonance, one that appears to siphon energy from one particle population to another without the usual accompanying thermal signals. This might be a mechanism unique to the strange hybrid zone it is exploring where solar and galactic forces meld. Moreover, this phenomenon points to the presence of unknown organizing forces. For waves to propagate in this manner and transfer energy without losing coherence over vast distances implies the existence of stable guiding structures. These might be filamentary magnetic fields or large-scale electric field configurations sustained by galactic currents. They may even represent the remnants of ancient shock waves or supernova remnants whose energies have been gradually absorbed into the interstellar medium. Whatever their source, the presence of such coherent, stable features in a supposedly chaotic part of space is deeply perplexing and exhilarating. The spacecraft has also detected what appear to be temporal oscillations in the density of interstellar particles, cyclic changes that suggest some kind of pulsing or beating pattern in the interstellar medium. These pulsations don't seem to align with solar activity or known galactic phenomena. Their periodicity suggests a source of regular influence that could be operating at scales previously unaccounted for. Some theories propose that this might be evidence of the solar system moving through a structured wave of interstellar gas, a ripple in the galactic arm, possibly caused by ancient gravitational perturbations or even exotic matter distributions such as dark matter filaments. Further complicating the picture is a form of spatial anisotropy, subtle directional differences in the behavior of both magnetic fields and particle flows. Rather than a uniform gradient from the Sun outward, Voyager 2 has revealed a twisted, lopsided shape to the boundary region. Some areas are compressed and active, while others appear diffuse and quiescent. This asymmetry suggests that external forces are exerting directional pressure on the heliosphere, shaping it like wind against a balloon. Intriguingly, the asymmetry doesn't align with the galactic plane or the Sun's motion, hinting at influences from sources that are either unrecognized or poorly understood, possibly interstellar shock fronts or magnetic anomalies far beyond the local region. The nature of time itself might also be behaving differently in this strange zone. Not in any science fiction sense, but in terms of relativistic time effects and how energy exchange is temporally resolved. Some data suggests that particle interactions are delayed beyond what simple travel times would indicate. Particles arrive with energy signatures that imply they should have interacted or decayed far earlier in their journey. This temporal dislocation might point to an unknown mechanism of time dilation or energy storage, perhaps involving the exotic plasma conditions in this region. Alternatively, it could indicate a kind of lag created by the peculiar properties of the field lines themselves, possibly through some form of energy echo or loop, or on top of these puzzling phenomena, Voyager 2 has transmitted evidence of low-frequency electromagnetic tones within the plasma, deep humming oscillations that suggest massive widespread coherence among the particles. These plasma tones, some of which fall within the audible range when converted to sound waves, form complex patterns reminiscent of standing waves in confined systems. Such coherence implies that the plasma is being contained or reflected in some way, potentially by large-scale structures or boundaries we cannot directly observe. If the interstellar medium can support standing plasma waves of this kind, it forces a reconsideration of how energy and information move through the galaxy at large. These coherent structures might also offer a form of natural propulsion or navigation for any future spacecraft traveling these routes. If such waves can carry energy efficiently across massive distances, then it might one day be possible to surf these waves, using them for low-energy travel. It's speculative, but the very fact that these patterns exist suggests they could be harnessed. More immediately, though, their discovery implies that interstellar space is far from empty. It is structured, resonant, and rich in dynamics we are only just beginning to understand. Perhaps most unnerving is a series of data anomalies related to temperature. Voyager 2 has recorded sharp, localized temperature shifts across seemingly stable regions. These are not gradual changes, but abrupt transitions, drops or spikes in temperature within tiny spatial scales, possibly spanning just a few kilometers. These shifts may indicate tiny, undetected boundary layers or shock fronts, microscopic analogs to weather fronts on Earth. If so, then the outer solar system is teeming with an unseen and unpredictable space weather, potentially more complex and dynamic than the inner solar system. This adds an entirely new dimension to our understanding of space hazards for future missions. Alongside the scientific conundrums, Voyager 2 has stirred philosophical and even metaphysical questions about the nature of boundaries themselves. What does it mean to exit the solar system? If the heliopause is neither fixed nor uniform, and if it interacts intimately with the interstellar medium, then crossing it might be more akin to entering a liminal zone than a sharp transition. Perhaps there is no true outside, just varying degrees of connectivity between the Sun and its galactic surroundings. This could lead to a redefinition of what constitutes the solar system itself, broadening it to include layers of influence and entanglement that extend far beyond what classical definitions allowed. The mathematical tools required to describe this complexity are now under revision. Fluid dynamics, magnetic field theory, and plasma physics are being retooled to incorporate nonlinear and non-equilibrium processes. Voyager 2's data shows that old models, especially those based on idealized symmetrical assumptions, failed to capture the chaotic richness of this frontier. New simulations must incorporate real-time feedback mechanisms, chaotic attractors, and even quantum-scale interactions given the energies and scales at play. These evolving models will shape the future of everything from space travel to astrophysical research to our understanding of the forces that govern star systems and planetary evolution. The idea of zones of influence is gaining traction, regions where the interaction between stellar and galactic forces creates unique conditions not reproducible elsewhere. The region Voyager 2 is traversing may be one such zone. It may host chemical interactions that produce novel compounds catalyzed by the unique mix of radiation, cold plasma, and interstellar dust. Organic precursors, building blocks of life, might form in such a space, accelerated by processes we can't replicate in laboratories. If this is the case, then the boundary of the solar system could also be a birthplace for life's chemical origins, not in the sense of Earth's biochemistry, but as a cosmic synthesis zone. Furthermore, Voyager 2's findings are beginning to illuminate a possibility that the boundaries between star systems are not merely passive gaps, but active agents of change. The solar system's movement through the galaxy involves passage through interstellar clouds, magnetic corridors, and radiation belts, each one potentially reshaping the conditions within the heliosphere. With the data now arriving, it's plausible that Earth has undergone cyclical exposure to such regions in the past, and might again. These cycles could leave signatures in geological records in ice cores or tree rings, hinting at epochs where the cosmic environment altered climate or radiation exposure significantly. The role of dark matter might also intersect with Voyager 2's findings. While dark matter remains undetected directly, some hypotheses suggest it could cluster in filaments or halo-like distributions around galaxies. If one such structure intersects with our region of the Milky Way, it might subtly warp spacetime or alter magnetic field propagation in ways that mimic some of Voyager 2's anomalies. This would give researchers a rare chance to see dark matter's effects through its indirect influence on interstellar plasma and magnetic orientation. Such a link, while speculative, adds another layer of urgency to the interpretation of these anomalies. Adding to the complexity is the idea that Voyager 2 is moving through a multi-phase environment, not just in plasma terms, but in chemical composition. Spectral analysis indicates traces of heavy elements and molecules that were not expected at such distances. These may be the remains of ancient supernova carried on galactic winds for millions of years. Their presence in Voyager's vicinity could imply that the outer solar system has been enriched by distant stellar deaths, infusing it with the byproducts of long-extinct stars. This adds a poetic resonance to the discovery. Voyager, a machine built by humans from stardust, is now traversing the ash of cosmic explosions that predate our very sun.